Let knowledge flow like a river without any hindrance. Don't make it like a stagnant pool. Hello everyone. I think all of you are okay. I am P.S. Chatterjee with today's presentation, Durability of Concrete, Commentary on IS 456-2000, Clause 8, this is part 15 of this series. Structural design only. A channel with different vision. This is our flow chart illustrating Clause 8 of IS 456-2000. Under this clause, we have two main sections, Clause 8.1 and Clause 8.2. Under Clause 8.2, we delve deeper into specific considerations with 8 subclauses, numbered 8.2.1 through 8.2.8. Furthermore, Clause 8.2.2 is subdivided into 4 clauses, denoted as 8.2.2.1 to 8.2.2.4. Similarly, Clause 8.2.3 is divided into 2 subclauses, 8.2.3.1 and 8.2.3.2. Additionally, Clause 8.2.4 consists of 2 subclauses, numbered 8.2.4.1 and 8.2.4.2. Clause 8.2.5 is subdivided into 4 subclauses, 8.2.5.1 through 8.2.5.4. Furthermore, Clause 8.2.6 is subdivided into 2 subclauses, 8.2.6.1 and 8.2.6.2. Finally, Clause 8.2.8 is subdivided into 4 subclauses, 8.2.8.1 through 8.2.8.4. This detailed breakdown allows us to thoroughly examine the various aspects related to durability outlined in Clause 8 of the standard. If you're tuning in for the first time, welcome. For a comprehensive understanding, consider starting from Part 01 for more information. Now, to all my new beautiful viewers, here's a small task for you. Before we dive into the lecture, please take a moment to like, share, and subscribe to my channel. It costs nothing to you, but it means the world to me and is a return gift for all the hard work put into creating this content. I hope. Clause 8, Durability of Concrete. What is durability of concrete? Clause 8.1 gives us a general idea of the durability of concrete. A durable concrete is one that performs satisfactorily in the working environment during its anticipated exposure conditions during service. The materials and mix proportions specified and used should be such as to maintain its integrity and, if applicable, to protect embedded metal from corrosion. Clause 8.1.1 One of the main characteristics influencing the durability of concrete is its permeability to the ingress of water, oxygen, carbon dioxide, chloride, sulfate and other potentially deleterious substances. Impermeability is governed by the constituents and workmanship used in making the concrete. With normal weight aggregates, a suitably low permeability is achieved by having an adequate cement content, sufficiently low free water/cement ratio, by ensuring complete compaction of the concrete, and by adequate curing. The factors influencing durability include: A. The environment. B. The cover to embedded steel. C. The type and quality of constituent materials. D. The cement content and water to cement ratio of the concrete. E. Workmanship, to obtain full compaction and efficient curing, and F. the shape and size of the member. These points are also important for the examination purposes. The degree of exposure anticipated for the concrete during its service life together with other relevant factors relating to mix composition, workmanship, design, and detailing should be considered. The concrete mix to provide adequate durability under these conditions should be chosen taking account of the accuracy of current testing regimes for control and compliance as described in the standard. Clause 8.2, Requirements for Durability. As I shown in my flow chart, this clause has 8 subclauses, from 8.2.1 to 8.2.8. Clause 8.2.1, Shape and size of member. The shape or design details of exposed structures should be such as to promote good drainage of water and to avoid standing pools and rundown of water. Care should also be taken to minimize any cracks that may collect or transmit water. Adequate curing is essential to avoid the harmful effects of early loss of moisture. See 13.5. Member profiles and their intersections with other members shall be designed and detailed in a way to ensure easy flow of concrete and proper compaction during concreting. Concrete is more vulnerable to deterioration due to chemical or climatic attack when it is in thin sections, in sections under hydrostatic pressure from one side only, in partially immersed sections and at corners and edges of elements. The life of the structure can be lengthened by providing extra cover to steel, by chamfering the corners or by using circular cross sections or by using surface coatings which prevent or reduce the ingress of water, carbon dioxide or aggressive chemicals. Clause 8.2.2, Exposure Conditions. Under Clause 8.2.2 there are 4 subclauses, Clause 8.2.2.1 to Clause 8.2.2.4. This is Clause 8.2.2.1, General Environment. The general environment to which the concrete will be exposed during its working life is classified into 5 levels of severity, that is, mild, moderate, severe, very severe and extreme as described in Table 3. Table 3 Environmental Exposure Conditions. It explains, the Clause 8.2.2.1 and Clause 35.3.2, here we are focusing on Clauses 8.2.2.1 only. In Table 3, we have 3 columns. Column number 1, it is serial number. Column number 2, it is environment. Column number 3, it is exposure conditions. Serial number 1, environment, mild, exposure condition, concrete surfaces protected against weather or aggressive conditions, except those situated in coastal area. Serial number 2, environment, moderate, exposure condition, concrete surfaces sheltered from severe rain or freezing, whilst wet concrete exposed to condensation and rain, concrete continuously under water, concrete in contact or buried under non-aggressive soil or groundwater, concrete surfaces sheltered from saturated salt air in coastal area. Serial number 3, environment, severe, exposure condition, concrete surfaces exposed to severe rain, alternate wetting and drying or occasional freezing whilst wet or severe condensation. Concrete completely immersed in sea water, concrete exposed to coastal environment. Serial number 4, environment, very severe, exposure condition, concrete surfaces exposed to sea water spray, corrosive fumes, or severe freezing conditions whilst wet, concrete in contact with or buried under aggressive subsoil or groundwater. Serial number 5, environment, extreme, exposure condition, surface of members in tidal zone, members in direct contact with liquid or solid aggressive chemicals. In this slide you are watching Clause 8.2.2.2 and Clause 8.2.2.3. Before we delve into Clause 8.2.2.2, I would like to draw your attention to a key term, abrasive. When we talk about abrasive surfaces in construction, we are referring to those that are rough, harsh, gritty, corrosive, or otherwise challenging to work with. Think of surfaces that scratch, feel coarse, erode, or require grinding. Now, in situations where we encounter such surfaces, it's crucial to understand how to address them effectively. This is where Clause 8.2.2.2 comes into play, providing valuable insights and guidelines. Let us explore its significance together. Clause 8.2.2.2 Abrasive, specialist literatures may be referred to for durability requirements of concrete surfaces exposed to abrasive action, for example, in case of machinery and metal tires. Clause 8.2.2.3 Freezing and thawing, where freezing and thawing actions under wet conditions exist. Enhanced durability can be obtained by the use of suitable air entraining admixtures. When concrete lower than grade M50 is used under these conditions, the mean total air content by volume of the fresh concrete at the time of delivery into the construction should be. When nominal maximum size of aggregate, 20 mm, expected entrained air percentage, 5% plus 1 or minus 1%. When nominal maximum size of aggregate 40 mm, expected entrained air percentage, 4% plus 1 or minus 1%. Since air entrainment reduces the strength, suitable adjustments may be made in the mix design for achieving required strength. In this slide, you will witness a discussion on Clause 8.2.2.4, the final subclause of Clause 8.2.2. This clause sheds light on how the presence of sulfate affects the concrete mix. Additionally, it touches upon Table 4, which will be featured in the next slide. Now, let's delve into Clause 8.2.2.4, Exposure to sulfate attack. Table 4 provides recommendations for the type of cement, maximum free water to cement ratio, and minimum cement content necessary at different sulfate concentrations in near neutral groundwater with a pH of 6 to 9. In cases of very high sulfate concentrations in Class 5 conditions, it is advisable to employ some form of lining such as polyethylene or polychloroprene sheeting, or surface coatings based on asphalt, chlorinated rubber, epoxy, or polyurethane materials to prevent access by the sulfate solution. This is our Table 4 as I mentioned in my last slide, requirements for concrete exposed to sulfate attack. Clauses 8.2.2.4 and 9.1.2. Currently, our focus is on Clauses 8.2.2.4. This table comprises 5 main columns and 5 rows. The first column is for serial numbers. The second column is for class designation. The third column is for concentration of sulfates, expressed as SO3, which further divides into 3 sub-columns. The first sub-column is for total SO3 in percentage. The second sub-column is for SO3 in 2:1 water to soil extract, measured in grams per liter. The third sub-column is for SO3 in groundwater, measured in grams per liter. The fourth column is for type of cement. The fifth column is for dense, fully compacted concrete made with 20 mm nominal maximum size aggregates complying with IS 383, which is further divides into two columns. The first sub-column is for minimum cement content in kilograms per cubic meter. The second sub-column is for maximum face water cement ratio. Serial number, italic 1. Class designation, 1. Total SO3, in percentage traces, less than 0.2%. SO3 in ratio of 2:1 water to soil extract, less than 1 grams per liter. SO3 in groundwater, less than 0.3 grams per liter. Type of cements, ordinary Portland cement, or Portland slag cement, or Portland pozzolana cement. Minimum cement content, 280 kilograms per cubic meter. Maximum face water cement ratio, 0.55. Serial number, italic 2. Class designation, 2. Total SO3, in percentage, 0.2 to 0.5%. SO3 in ratio of 2:1 water to soil extract, 1 to 1.9 grams per liter. SO3 in groundwater, 0.3 to 1.2 grams per liter. Type of cements, ordinary Portland cement, or Portland slag cement, or Portland pozzolana cement. Minimum cement content 330 kilograms per cubic meter. Maximum face water cement ratio, 0.5. Type of cements, supersulfated cement, or sulfate-resisting Portland cement. Minimum cement content 310 kilograms per cubic meter. Maximum face water cement ratio, 0.5. In this slide, we will continue discussing Table 4, Requirements for Concrete Exposed to Sulfate Attack, Clauses 8.2.2.4 and 9.1.2. Serial number, italic 3. Class designation, 3. Total SO3, in percentage, 0.5 to 1%. SO3 in ratio of 2:1 water to soil extract 1.9 to 3.1 grams per liter. SO3 in groundwater, 1.2 to 2.5 grams per liter. Type of cements, supersulfated cement, or sulfate-resisting Portland cement. Minimum cement content 330 kilograms per cubic meter. Maximum face water cement ratio, 0.5. Type of cements, Portland pozzolana cement or Portland slag cement. Minimum cement content 350 kilograms per cubic meter. Maximum face water cement ratio, 0.45. Serial number, italic 4. Class designation, 4. Total SO3, in percentage, 1 to 2%. SO3 in ratio of 2:1 water to soil extract, 3.1 to 5 grams per liter. SO3 in groundwater, 2.5 to 5 grams per liter. Type of cements, supersulfated or sulfate-resisting Portland cement. Minimum cement content 370 kilograms per cubic meter. Maximum face water cement ratio, 0.45. Serial number, italic 5. Class designation, 5. Total SO3, in percentage, more than 2%. SO3 in ratio of 2:1 water to soil extract, more than 5 grams per liter. SO3 in groundwater, more than 5 grams per liter. Type of cements, sulfate-resisting Portland cement, or supersulfated cement with protective coatings. Minimum cement content 400 kg per cubic meter. Maximum face water cement ratio, 0.4. Below Table 4, there are 7 important notes regarding requirements for concrete exposed to sulfate attack. They are as follows. 0.1 Cement content given in this table is irrespective of grades of cement. 0.2 Use of supersulfated cement is generally restricted where the prevailing temperature is above 40 degrees Celsius. 0.3 Supersulfated cement gives an acceptable life provided that the concrete is dense and prepared with a water-cement ratio of 0.4 or less, in mineral acids, down to pH 3.5. 0.4 The cement contents given in column 6 of this table are the minimum recommended. For sulfate contents near the upper limit of any class, cement contents above these minimum are advised. This slide continues the discussion of notes below Table 4. 0.5 For severe conditions, such as thin sections under hydrostatic pressure on one side only and sections partly immersed, considerations should be given to a further reduction of water-cement ratio. 0.6 Portland slag cement conforming to IS 455 with slag content more than 50% exhibits better sulfate-resisting properties. 0.7 Where chloride is encountered along with sulfates in soil or groundwater, ordinary Portland cement with C3A content from 5 to 8% shall be desirable to be used in concrete, instead of sulfate-resisting cement. Alternatively, Portland slag cement conforming to IS 455 having more than 50% slag or a blend of ordinary Portland cement and slag may be used provided sufficient information is available on performance of such blended cements in these conditions. Additionally, C3A stands for tricalcium aluminate. On this slide, we're focusing on Clause 8.2.4, which deals with concrete mix proportions. Within Clause 8.2.4, there are 2 subclauses, namely 8.2.4.1 and 8.2.4.2. Let's begin by examining Clause 8.2.4.1. Clause 8.2.4.1 General. The free water-cement ratio is an important factor in governing the durability of concrete and should always be the lowest value. Appropriate values for minimum cement content and the maximum free water-cement ratio are given in Table 5 for different exposure conditions. The minimum cement content and maximum water-cement ratio apply to 20 mm nominal maximum size aggregate. For other sizes of aggregate they should be changed as given in Table 6. Cement content not including fly ash and ground granulated blast furnace slag in excess of 450 kg per cubic meter should not be used unless special consideration has been given in design to the increased risk of cracking due to drying shrinkage in thin sections, or to early thermal cracking and to the increased risk of damage due to alkali-silica reactions. In the preceding slide, I introduced 2 tables, Table 5 and Table 6. Let's focus on Table 5. This table provides insights into the appropriate values for minimum cement content and the maximum free water-cement ratio across various exposure conditions. The title of Table 5 is Minimum Cement Content, Maximum Water-Cement Ratio, and Minimum Grade of Concrete for different exposures with normal weight aggregates of 20 mm nominal maximum size, referencing clauses 6.1.2, 8.2.4.1, and 9.1.2. Table 5 comprises 4 main columns and 5 rows. The first column serves as a serial number identifier, while the second column delineates exposure conditions. Moving to the third column, it addresses plain concrete, further subdivided into 3 subcolumns. These subcolumns detail the minimum cement content, in kilograms per cubic meter, the maximum face water to cement ratio, and the minimum grade of concrete required. Similarly, the fourth column focuses on reinforced concrete, also divided into 3 subcolumns. Here, we find specifications for minimum cement content, maximum face water to cement ratio, and minimum grade concrete, pertinent to reinforced concrete structures. Serial number 1. Exposure, mild. Plain concrete, minimum cement content 220 kilograms per cubic meter. Maximum face water to cement ratio, 0.6, grade of concrete, non-specific. And for reinforced concrete, minimum cement content 300 kilograms per cubic meter. Maximum face water to cement ratio, 0.55, grade of concrete. M20. Serial number 2. Exposure, moderate. Plain concrete, minimum cement content 240 kilograms per cubic meter. Maximum face water to cement ratio, 0.6, grade of concrete. M15. And for reinforced concrete, minimum cement content 300 kilograms per cubic meter. Maximum face water to cement ratio, 0.5, grade of concrete. M25. Serial number 3. Exposure, severe. Plain concrete, minimum cement content 250 kilograms per cubic meter. Maximum face water to cement ratio, 0.5, grade of concrete. M20. And for reinforced concrete, minimum cement content 320 kilograms per cubic meter. Maximum face water to cement ratio, 0.45, grade of concrete. M30. Serial number 4. Exposure, very severe. Plain concrete, minimum cement content 260 kilograms per cubic meter. Maximum face water to cement ratio, 0.45, grade of concrete. M20. And for reinforced concrete, minimum cement content 340 kilograms per cubic meter. Maximum face water to cement ratio, 0.45, grade of concrete. M35. Serial number 5. Exposure, extreme. Plain concrete, minimum cement content 280 kilograms per cubic meter. Maximum face water to cement ratio, 0.4, grade of concrete. M25. And for reinforced concrete, minimum cement content 360 kilograms per cubic meter. Maximum face water to cement ratio, 0.4, grade of concrete. M40. Below Table 5, there are 2 important notes to consider. Note 1. The cement content provided in this table is independent of cement grades and includes any additives mentioned in Clause 5.2. Additives such as fly ash or ground granulated blast furnace slag may be incorporated into the concrete mix regarding cement content and water-cement ratio, provided their suitability is confirmed. However, the total amount of additives must not exceed the limits specified in IS 1489, Part 1, for pozzolana and in IS 455 for slag. Note 2, it's worth noting that the minimum grade for plain concrete under mild exposure conditions is not specified. On this slide, you'll encounter Table 6, which details adjustments to minimum cement contents for aggregates other than 20 mm nominal maximum size, as per Clause 8.2.4.1. Additionally, Clause 8.2.4.2 addresses maximum cement content. Table 6 consists of 3 columns and 3 rows. The first column functions as a serial number identifier. In the second column, the nominal maximum aggregate size is specified in millimeters. Transitioning to the third column, it pertains to the adjustments to minimum cement contents as outlined in Table 5, expressed in kilograms per cubic meter. Serial number 1. Nominal maximum aggregate size 10 mm, adjustable to minimum cement contents in Table 5, plus 40 kilograms per cubic meter. Serial number 2. Nominal maximum aggregate size 20 mm, adjustable to minimum cement contents in Table 5, 0 kilograms per cubic meter. Serial number 3. Nominal maximum aggregate size 40 mm, adjustable to minimum cement contents in Table 5, minus 30 kilograms per cubic meter. Now it is Clause 8.2.4.2. Maximum cement content not including fly ash and ground granulated blast furnace slag in excess of 450 kilograms per cubic meter. Should not be used unless special consideration has been given in design to the increased risk of cracking due to drying shrinkage in thin sections, or to early thermal cracking and to the increased risk of damage due to alkali-silica reactions. In this slide, I will be discussing Clause 8.2.5.1 titled, General and Clause 8.2.5.2 titled, Chlorides in Concrete, which are part of Clause 8.2.5 Mix Constituents. Clause 8.2.5.1 General, for concrete to be durable, careful selection of the mix and materials is necessary, so that deleterious constituents do not exceed the limits. Clause 8.2.5.2 Chlorides in concrete. Whenever there is chloride in concrete there is an increased risk of corrosion of embedded metal. The higher the chloride content, or if subsequently exposed to warm moist conditions, the greater the risk of corrosion. All constituents may contain chlorides and concrete may be contaminated by chlorides from the external environment. To minimize the chances of deterioration of concrete from harmful chemical salts, the levels of such harmful salts in concrete coming from concrete materials, that is, cement, aggregates, water and admixtures, as well as by diffusion from the environment should be limited. The total amount of chloride content in the concrete at the time of placing shall be as given in Table 7. The total acid-soluble chloride content should be calculated from the mix proportions and the measured chloride contents of each of the constituents. Wherever possible, the total chloride content of the concrete should be determined. This is our Table 7, based on Clause 8.2.5.2 and title of this table is, Limits of Chloride Content of Concrete. In this table we have 3 columns and 3 rows. Column 1, Serial Number. Column 2, represents, type or use of concrete, and column 3 stands for maximum total acid-soluble chloride content expressed as kg per cubic meter of concrete. Serial number 1, type or use of concrete, concrete containing metal and steam cured at elevated temperature and pre-stressed concrete. Maximum total acid-soluble chloride content, 0.4 kg per cubic meter of concrete. Serial number 2, type or use of concrete, reinforced concrete, or plain concrete containing embedded metal. Maximum total acid-soluble chloride content, 0.6 kg per cubic meter of concrete. Serial number 3, type or use of concrete, concrete not containing embedded metal or any material requiring protection from chloride. Maximum total acid-soluble chloride content, 3 kg per cubic meter of concrete. In this slide, I will be discussing on two clauses, Clause 8.2.5.3, titled, Sulfates in Concrete, and Clause 8.2.5.4, titled, Alkali Aggregate Reaction, which are part of Clause 8.2.5 Mix Constituents. Clause 8.2.5.3 Sulfates in concrete. Sulfates are present in most cements and in some aggregates. Excessive amounts of water-soluble sulfate from these or other mix constituents can cause expansion and disruption of concrete. To prevent this, the total water-soluble sulfate content of the concrete mix, expressed as SO3, should not exceed 4% by mass of the cement in the mix. The sulfate content should be calculated as the total from the various constituents of the mix. The 4% limit does not apply to concrete made with supersulfated cement complying with IS 6909. Clause 8.2.5.4 Alkali Aggregate Reaction. Some aggregates containing particular varieties of silica may be susceptible to attack by alkalis, N2O and K2O, originating from cement or other sources, producing an expansive reaction which can cause cracking and disruption of concrete. Damage to concrete from this reaction will normally only occur when all the following are present together. This slide is continuation of Clause 8.2.5.4, titled, Alkali Aggregate Reaction, which are part of Clause 8.2.5 Mix Constituents. A high moisture level, within the concrete. B. A cement with high alkali content, or another source of alkali. C. Aggregate containing an alkali reactive constituent. Where the service records of particular cement/aggregate combination are well established, and do not include any instances of cracking due to alkali aggregate reaction, no further precautions should be necessary. When the materials are unfamiliar, precautions should take one or more of the following forms. A. Use of non-reactive aggregate from alternate sources. B. Use of low alkali ordinary Portland cement having total alkali content not more than 0.6%, as Na2O equivalent. Further advantage can be obtained by use of fly ash, grade 1, conforming to IS 3812, or granulated blast furnace slag conforming to IS 12089 as part replacement of ordinary Portland cement, having total alkali content as Na2O equivalent not more than 0.6%, provided fly ash content is at least 20% or slag content is at least 50%. Precautions for unfamiliar materials, continued. C. Measures to reduce the degree of saturation of the concrete during service, such as use of impermeable membranes. D. Limiting the cement content in the concrete mix and thereby limiting total alkali content in the concrete mix. For more guidance, specialist literatures may be referred. Concern: some aggregates, particularly those with specific silica varieties, can be vulnerable to alkali aggregate reaction, AAR, from sources like cement, leading to concrete cracking and disruption. Conditions for damage: damage typically occurs when several factors align. A. Use of non-reactive aggregate from alternate sources. B. Use of low alkali ordinary Portland cement having total alkali content not more than 0.6%, as Na2O equivalent. C. Further advantage can be obtained by use of fly ash, grade 1, conforming to IS 3812 or granulated blast furnace slag conforming to IS 12089 as part replacement of ordinary Portland cement, having total alkali content as Na2O equivalent not more than 0.6%, provided fly ash content is at least 20% or slag content is at least 50%. D. Measures to reduce the degree of saturation of the concrete during service such as use of impermeable membranes. E. Limiting the cement content in the concrete mix and thereby limiting total alkali content in the concrete mix. For more guidance, specialist literatures may be referred. In this slide, I am going to discuss on clause 8.2.6. Concrete in aggressive soils and water. Under this clause we have two subclauses, 8.2.6.1 and 8.2.6.2. First clause 8.2.6.1 and the note associated with this. 8.2.6.1 General: the destructive action of aggressive waters on concrete is progressive. The rate of deterioration decreases as the concrete is made stronger and more impermeable, and increases as the salt content of the water increases. Where structures are only partially immersed or are in contact with aggressive soils or waters on one side only, evaporation may cause serious concentrations of salts with subsequent deterioration, even where the original salt content of the soil or water is not high. Note: guidance regarding requirements for concrete exposed to sulfate attack is given in 8.2.2.4. In clause 8.2.6.2, drainage: at sites where alkali concentrations are high or may become very high, the groundwater should be lowered by drainage so that it will not come into direct contact with the concrete. Additional protection may be obtained by the use of chemically resistant stone facing or a layer of plaster of Paris covered with suitable fabric, such as jute thoroughly impregnated with bituminous material. Now it is, clause 8.2.7, compaction, finishing and curing. Adequate compaction without segregation should be ensured by providing suitable workability and by employing appropriate placing and compacting equipment and procedures. Full compaction is particularly important in the vicinity of construction and movement joints and of embedded water bars and reinforcement. In clause 8.2.7, titled Compaction, Finishing, and Curing, emphasis is placed on the significance of good finishing practices for ensuring durable concrete. It's advised to refrain from overworking the surface or adding excess water or cement during finishing, as this can result in weakened strength and durability, especially vulnerable to freezing and thawing in wet conditions due to the formation of lands. Furthermore, proper and adequate curing techniques are highlighted as essential for reducing concrete permeability and enhancing durability. Effective curing extends the hydration of the cement, particularly crucial for the surface zone of the concrete, refer to clause 13.5, to ensure optimal strength and durability. Clause 8.2.8 Concrete in seawater. Concrete in seawater or exposed directly along the sea coast shall be at least M20 grade in the case of plain concrete and M30 in case of reinforced concrete. The use of slag or pozzolana cement is advantageous under such conditions. Under this clause we have four subclauses: 8.2.8.1, 8.2.8.2, 8.2.8.3 and 8.2.8.4. In this slide, we'll delve into the subclauses of clause 8.2.8. These clauses are essential in ensuring the durability and longevity of concrete structures. Clause 8.2.8.1. Special attention shall be given to the design of the mix to obtain the densest possible concrete. Slag, broken brick, soft limestone, soft sandstone, or other porous or weak aggregates shall not be used. Clause 8.2.8.2. As far as possible, preference shall be given to precast members unreinforced, well cured and hardened, without sharp comers, and having trowel smooth finished surfaces free from crazing, cracks, or other defects. Plastering should be avoided. Clause 8.2.8.3. No construction joints shall be allowed within 600 mm below low water level or within 600 mm of the upper and lower planes of wave action. Where unusually severe conditions or abrasion are anticipated, such parts of the work shall be protected by bituminous or silica fluoride coatings or stone facing bedded with bitumen. Clause 8.2.8.4. In reinforced concrete structures, care shall be taken to protect the reinforcement from exposure to saline atmosphere during storage, fabrication, and use. It may be achieved by treating the surface of reinforcement with cement wash or by suitable methods. And with that, we conclude the commentary on IS 456, 2000, Part 15, of this series. I trust you found this video informative and engaging. Stay tuned for my next video, which will delve into Clause 9, Concrete Mix Proportioning. Remember to subscribe to my channel for more content like this. Your likes, shares, subscriptions, and comments serve as great motivation for me to keep creating. Thank you for watching.